Okay, so the title of the chapter is Angular Momentum. Okay, you learned linear momentum earlier in one of the previous chapters. It was linear momentum was denoted by P, and that was mass times velocity of the object. Now we are going to study angular momentum denoted by L. It's a vector, and here's the definition. You're calculating the angular momentum about a point, and R is the how far the object is. That's the position vector of the object with reference to this point cross P. All right, and you'll see angular momentum will be, so just like this formula, for a rigid object, angular momentum will be given by that. Okay, mass gets replaced by the moment of inertia, linear velocity gets replaced by angular velocity. Okay. Can anybody tell me what is Newton's second law? I'm sorry? Very good. Force is dp time rate of change of momentum. Okay, similarly, torque that causes rotational motion will be time rate of change of angular momentum. So this is Newton's second law for rotational motion. Okay. So that is the goal. Okay, so you'll study all of this. Now, when does this guy reduce to F equal to ma? Very good, my friend. When the mass of the object is constant. Okay, and that's not true for a rocket. So that's true for when you're driving your car. Okay. So similarly, what is the parallel of mass? When the moment of inertia is constant, then this torque will be I times alpha. Okay. When can torque change? When can moment of inertia change? If an object is spinning and an ice skater spinning, and you move your arms back and forth, the moment of inertia is changing. Okay, you're moving the mass distribution with respect to the mass distribution is changing with respect to the axis of rotation. Okay, so that happens often. But if it's a rigid object, then the moment of inertia won't be changing. Okay. All right, so that's what this chapter is about. So again, I'm going to try and go through the slides fairly quickly. Okay. What this shows you is, this is the path traced by points on the rim of a rolling wheel. Okay, rolling without slipping are cycloids. Okay, so a wheel rolling at constant velocity, whose center of mass is going at constant velocity. The point on a rim, what that's showing is, if you put a light on the rim as this wheel rolls, that point, that light, the curve it traces is a cycloid. Okay, you might have heard of this curve in your calculus classes. Has anybody heard this term? Cycloid. All right, well, now you have. Okay? And this makes sense. You can trace this using a bicycle wheel. Okay? That's a cycloid. Okay? And you can see that the wheel is rolling at constant velocity because these are equal time intervals. All right, rolling motion without slipping is a combination of rotation and translation. Okay, so here is pure translation. In pure translation, every point is going at the same velocity. Here is pure rotation. In pure rotation, points on opposite ends have this opposite velocities. Okay. Now let's combine these two guys. This velocity plus that velocity is that velocity. This plus that is that. This plus this is that. So when a wheel is rolling without slipping, the point that is on contact with the ground, that's at rest momentarily. Okay. This guy is moving at twice the velocity of the center of mass. velocity. Okay. So this is a snapshot. So you can see that rolling motion is a combination of these two. Okay. So when a wheel is rolling without slipping, when the wheel rotates through an angle theta, the distance it travels is r theta, which is s. Okay. S, the distance it travels is r theta. And now you can take the time derivative of this. If you take the time derivative of s, you get the center of mass velocity, the velocity at which your car is going, okay, is the radius of the wheel is not changing, so r d theta by dt, so r omega. Okay. So the center of mass velocity, which we've seen already, is r for a rolling motion. It's r times omega, the angular velocity, the rate at which the wheel is turning. Okay. And similarly, the center of mass acceleration is r times alpha. Okay, you just take the time derivative again. Okay, what this shows is, as the wheel is rolling, the kinetic energy of the wheel is the kinetic energy of this piece plus the kinetic energy of this piece plus the kinetic energy of that piece, and so on. Okay, the wheel is rotating at an angular velocity omega. So the kinetic energy is 1/2 the moment of inertia of the wheel about this point, omega squared. Okay, omega is angular velocity about that point. And this, using the parallel axis theorem, the moment of inertia of the wheel about this point, perpendicular to that surface, is moment of inertia about the center of mass plus the mass of the wheel times r squared. This is for a disk. And for a uniform disk. So you can show that this is equal to the kinetic energy is the kinetic energy of pure rotation about that axis plus the kinetic energy of pure translation. Yeah. Again, this formula just shows you that rolling without slipping is translation plus rotation. Okay. So many might not know this. When you accelerate in your car, what makes you accelerate?
The force of friction with your wheel on the ground.
Yep. So what you're trying to do is you're trying to rotate the wheel faster and faster. But remember, this point was not slipping. That's at rest. What is preventing it from slipping, if you want to go that way, what's preventing it? It's the static friction force. Okay, so it's the static friction force that's propelling you, accelerating you forward. So I don't know if you guys have watched Hot Rod, the quarter-mile hot rod race on TV and stuff. They'll burn their tires before they take off. What are they trying to do?
Increase the static coefficient of friction.
That's right. Okay, they're trying to melt the rubber so they can increase the static coefficient of friction so they can take off. They can have greater acceleration. Okay. All right, so the static coefficient of friction is equal to mass times the acceleration of the center of mass. Okay, so what this is showing you is, if you have a disk rolling down a ramp, okay, now again, as this thing rolls down, this point is not, this is at rest. See, the wheel wants to slide down. What's preventing it from sliding down is the static coefficient of friction. Okay? So you have to have the static coefficient of friction, the static friction force to make it roll down. Okay. What this formula tells you is the following. So if you had an ice cube sliding down without friction down an incline, its acceleration would be g sine theta. Okay. Let me this over here. Okay, so for an ice cube sliding without friction, the acceleration is g sine theta. Okay, now you take a disk or a bowling ball or whatever, and it rolls down a ramp without slipping. You see its acceleration is g sine theta, that for the ice cube, but less by this factor. Okay, so here is a factor that's is greater than 1, so its acceleration is smaller than that. So if you raise an ice cube versus a wheel rolling down, the ice cube will reach the ground first. Okay, so that's what this is. So here are 3 objects: a disk, a ring, and a sphere, a solid sphere. Okay. They all have the same mass, same radius, and if you raise them down, the question is which one will reach the bottom first. Okay, so using this previous formula, you can solve this, well, also, or you can solve it different ways. Well, the potential energy, they all have the same potential energy. All that gets converted to kinetic energy, rotational kinetic energy plus translational kinetic energy. Okay, and you can calculate the velocity at the bottom. The velocity is 2gh, 1 over I center of mass divided by mr squared. This is the same. So the guy with the largest center of moment of inertia about the center of mass reaches last. Okay. So this guy has greater moment of inertia than this guy. So this guy will reach after him. Okay. And so the moment of inertia of this guy, I believe, is 2/5 or something like that, 2/5 mr squared. And for this guy, it's 1/2 mr squared. Okay. So this guy, he has that smaller moment of inertia than him. So he will definitely reach before him. Okay, so, and this guy is more than him. So this guy will reach first, second, third. Yeah. All right. So here is let's say a merry-go-round. You apply a force at this point in this direction, and you're calculating torques about the origin, about the center, about this point. Okay? The torque is defined as r, this vector, r the vector to the point of application of the force cross F. So the torque is r cross F, and this force will rotate this object counterclockwise. If this angle was 0, the torque would be 0, and the object would not rotate. Angular momentum is defined by L, and it's R cross P. Okay, so if this piece has a mass of mi, and its velocity is vi, its momentum is mi vi, and R cross P will give it the angular momentum of this piece about that point. Okay. So what this slide shows you is, remember Newton's second law for linear motion was dp by dt. What we're going to show is torque is dl by dt. Okay. For rotational motions, linear forces get replaced by torques. Linear momentum gets replaced by angular momentum. Okay. So it's the same formula applied for rotational motion. And we are going to show this derivation for a very simple case. Okay. But then it applies in the general case. So let's imagine here's a particle going in that direction, and and you apply, well, there's a particle and you apply a force in that direction. We're going to calculate torques about that point, about O. So here's the position, there's the vector to the point of application of the force. So R cross the force is the torque on this object about that point. The torque is R cross dP by dt. The force is dP by dt. Yeah. All right, this is R dP by dt. Okay, what we'd like to do is, we'd like to write this as dt R cross P. Well, what is this guy? From the chain rule, this is if R were a function of time, P were a function of time. By the chain rule, this would be dR by dt cross P equal to plus R cross dP by dt. Well, what is this guy? R is, dR by dt is velocity. Velocity is momentum over divided by mass. So this is momentum divided by mass cross P plus R cross dP by dt. Well, what is a vector crossed with itself? Anybody remember what's A cross A? What is it?
2A.
A cross A.
0.
0. Very good. See, if you have a vector A and a vector B, the magnitude of A cross B is A B sine theta. Okay? And if theta is 0, sine 0 is 0. So A cross A would be 0. This guy is 0. So you can add this to this. So this guy, you can add to that guy, you can add this guy for free, because this guy is 0. And this plus this is equal to that. So the net torque is equal to that, which is dL by dt. There's your Newton's second law. Okay. Again, don't worry about it. I just want you to remember that. Okay. The torque acting on an object, on a just like this applies to a single particle and it applies to a system of particles, just like that, this one applies to a single object and it applies to a system of objects. So the total momentum of a system of particles is the total angular momentum, sum of the angular momenta, okay. And you're calculating about the same point. And the time rate of change of the total angular momentum is equal to the net torque acting on the system. Okay. The net torque is just the torques acting on individual particles of the system. Okay, so here's a system. They're showing you a force acting on the system. But let's say if the system had, I'm just making up this example. Let's say it had charged particles. These guys would exert internal forces on each other. But these internal forces, so their torques would add up to 0. So the net torque on the system is the torque due to internal forces plus the torque due to external forces. The torque due to internal forces always add up to 0. Yep. So the net torque acting on a system is just the torque due to external forces. So here is Newton's second law. On a system, the torques due to external forces is equal to time rate of change of angular momentum of the system. Okay. And this formula has spectacular applications, okay? Because in general, the random forces that come in play in nature, their external torque will be zero. So for a lot of systems, you'll see that the angular momentum of the system remains constant. Okay, and so we'll see examples of that. So random forces will always end up applying zero torque, okay? Okay, so the relationship between torque and angular momentum is independent of the choice of the origin if the center of mass of the system is not accelerating. Okay. So what this statement, both torque and angular momentum depend on the choice of the origin of the coordinate system. So to apply this equation, of course, you have to calculate the torque about the same point, angular momentum about the same point. Okay, you can't calculate them about different points. Okay? For an axis passing through the center of mass, net torque acting on a system equals the time rate of change of angular momentum regardless of the motion of the center of mass. As long as you're calculating everything for an axis passing through the center of mass, this will always apply. Okay? So the angular momentum, now we'll consider a particle moving in a circle at constant speed. Okay. The angular momentum is r cross p. R is this vector, p is a vector in that direction. And you can see that if you use your right hand, R is in this direction, P is in that direction, L is coming out of the sheet of the paper. Okay. So R is in this direction, you rotate from R to P, angular momentum is coming out of the sheet. Okay. And the magnitude of the angular momentum is mvr. Okay. For a particle going in a circular path, the angular momentum is mvr. So for a rotating rigid object, for a rotating disk, the angular momentum of this particle is that, and for the entire disk, you just sum up over all the particles, and when you sum these all up, what you get is the total angular momentum is the sum of the angular momentum of all these particles. That turns out to be the moment of inertia of the disk about that axis times the angular velocity. So for a rigid object, L is I omega, and this is the parallel of this formula, mass times velocity. Okay. So the angular momentum is I times omega, and torque is I d omega by dt. So this is true, is I times alpha as long as I is not changing. Just like F equal to dp by dt, this was equal to ma when mass was constant. Similarly, torque is dl by dt, and that's equal to I times alpha as long as I is not changing. Okay. I'll just briefly mention the stop deal. What will happen if I let go?
Oh, it's gonna fall.
So here was the force of gravity acting on the center of mass. We're calculating the torque about that point. When this guy was not spinning, that torque made it fall like that. As soon as you gave it angular velocity, that same torque made it precess. Okay. So that's called precession. The faster it's spinning, the slower the precession. Okay? I'm going to show that to you in a second. I'll be back in a second. Here's a very spectacular example of that phenomenon of precession. Okay. Again, so you saw that when a torque acts on an object and if it's not spinning, well, it just falls down. Okay. As soon as it's spinning, it starts precessing. The Earth is spinning. It's a spinning top. And the gravity of the moon and the sun is trying to topple the Earth this way. There's a torque acting on the Earth. If it was a perfect sphere, that would not be true. So, the Earth's axis is precessing. How do we know the Earth's axis is precessing? All right. So this is the Earth. There's the sky. And you see objects in the sky rise and set. What's really happening is the Earth is rotating. What is the only point in the sky that is not moving? Or 2 points in the sky?
Poles.
The poles. That star, the North Star, whatever is that. Yeah. Now, if the axis is precessing, over time, the North Pole should change. The North Star should change. Okay. The Iraqi people were very good astronomers, so they had awesome records. There's the North Star today. Okay, so as the Earth precesses, the North Star is changing. that was the North Star. That's the North Star today. That was the North Star 5,000 years ago. The Earth precesses once in 26,000 years. Okay, so what does that mean? So here's the summer is in northern hemisphere now, in June. In 13,000 years, the axis will be pointing this way. So come back 13,000 years from now, and you can have winter in Florida in June. And it'll be summer in Ecuador in June. Okay. Yep.
Has there been evidence of that happening in the past?
Yeah. Well, this is the evidence. Yep. Every 26,000 years. Okay. So that's precession. Okay. All right. So a spinning top will precess. Okay. So it'll precess like that, and capital omega is the precession angular velocity, and little omega is the spinning velocity. Okay, so here I'm showing this derivation is for that bicycle wheel that I showed you. You spin the bicycle wheel and it precesses like that. Okay, and the precession angular velocity is mgr divided by I omega. Omega is the rate at which it's spinning. The faster it spins, the slower it precesses. Okay. All right. If you have cats, you can do this fun stuff. Okay. Okay. So we saw that the external torque is equal to dl by dt. And if the external torque is 0, dl by dt is 0, L is constant. The angular momentum of the system is constant if the external torque acting on the system is 0. Okay, so apparently this works. If you take a cat, hold it by its leg and not get scratched, and drop it from 3 feet, it'll land on its feet. Okay, so what physics is saying is the angular momentum of the cat, the total angular when you dropped it, the angular momentum was 0. What is the angular momentum as it's falling? 0. It's 0 all the way through. So how does it land on its feet? So its feet are up in the air, it's got to turn and land on its feet. So the cat is smart. It turns its front body one way and the rear turns the other way. Or the tail, so it has to have a tail. Okay? And it lands on its feet. But its total angular momentum is 0 through its entire fall. And this YouTube video, actually, some guys actually took the video and let's see if I can. All right, you guys can go look at the video. All right, you guys know why we throw a football with spin?
It's more stable in the air while it travels.
All right, so the reason you throw it is, okay, so the fastest computer in the world is attached to your shoulder. And when you throw a ball, so let's say in windy condition, if it wobbles, the drag forces change on the ball. Okay? If it maintained the same orientation, the drag forces would be fairly constant, and this computer can calculate where it will fall. By the way, this computer is doing real-time corrections. But if it's wobbling, that's not fast enough to calculate where it will fall. But if the orientation is steady, even with drag forces, you can calculate where it will fall and go run and catch it. Okay. So that's why you throw it with spin. Okay, so here's a quarterback, a right-hand quarterback, giving it spin, and there's the angular momentum. Okay. And that angular momentum, the wind does not apply any external torque on it, so this angular momentum remains constant. And this trajectory is easy to calculate even with drag forces present. Okay. So here's a system where the moment of inertia is changing. The moment of inertia is smaller here than there. There's no external torque acting on the system, so the angular momentum remains constant. So if she's spinning like that, initially her moment of inertia is great, and when she brings her arms in, the moment of inertia decreases and she spins faster. Okay. Same thing here. Okay, if this merry-go-round is spinning, and if this guy walks in toward this axis, what will happen?
The whole thing will spin faster.
Yeah, so it's the same thing as that, just like this system. The moment of inertia is decreasing, and angular velocity will increase. Yeah. All right. This is very good. Let me go get. Okay, so all I'm doing is this. The floor is not flat. Okay, so if the floor was flat and this was completely horizontal, you shouldn't be able to twist. Okay? Because, why? Because my angular momentum is zero and there's no external torque acting on it. And my angular momentum should be zero, no matter what you do. This is not crazy stuff. If this were a satellite up there, you want to turn the satellite, you turn a gyro in there and make the satellite spin. this were a satellite. I want the satellite to turn this way. I turn the gyro this way. Soon as I have turned enough, stop this, that will stop. You want to turn the satellite this way. You want to turn the satellite this way. Turn this. All right, so angular momentum has spectacular applications. Okay. What was going on here?
You were rotating in the opposite direction of the wheel.
Okay, so so here was the person. Okay, this was spinning that way. So let's say the total angular momentum for this system is 20 units. Okay. And then when you flip the wheel was rotating this way, and its angular momentum is minus 20 units. So the person had to spin in that direction with a momentum of 40 units, angular momentum of 40 units. This plus this was equal to that. Okay. These divers do the same thing. When you jump off, you give yourself a little angular momentum. And if you want to make 3 spins before you hit water, you scrunch yourself, decrease your momentum, spin faster, and hit the water. If you only want to spin twice, you don't scrunch yourself as much. Your angular velocity is not that great, and okay, you take 2 spins before you hit water. So here's how you turn satellites. Here's the gyro rotating this way. The satellite turns that way. So our solar system formed about 5 billion years ago, and if the solar system is this big, so do you know what is this distance? Uh, 100 million miles. Okay, this is 1 AU, and the furthest planet is about 30 AU. So if the Earth was this far away, Neptune is about that far away. Okay, so the solar system would be as large as this room. The solar system formed from a cloud 5 billion years ago that was as big as this campus. You know, Dunn Avenue and ISB. So from that, it collapsed to this. Essentially all the masses in the sun. That cloud was rotating slowly initially. Okay. And that angular momentum has remained constant for 5 billion years. Okay. And that's the sun is spinning and the planet's going around. All right, there's other stories, but